primary sensing element. We have variable conversion, which is the transducers, and then you have the signal processing, which is the Arduino. You can transmit the data, output it, and then you can have a feedback for the subject to do whatever. And also you can do stimulation to the subject, like changing temperature or changing colors and see what happened to that measurement. Or for example, let me see this here when you affect the measurement. So let's say someone is taking a drug, and that drug is affecting the heart rate, right? So I'm stimulating my measurement. Or someone is taking a sleeping pill, sleep apnea. So the stimulation, part is transducers. See this here, one form of energy to another form of energy. It's very important. And usually we try to our forms of energy that we would like to work with to be electrical. So it's either voltage or current. And that's why we covered those at the beginning of the class. People are interested in measure in the human body, but we have things that are those difficult to assess, right? And they usually need to have an invasive way to measure those. And actually in one of those. So you can say, well, I would like to be a biomedical engineer who knows everything about the instruments related to biopotential. And we call you, when we do this, we call you, because you know all of these things. Flow of blood and fluids inside the body, dimensions, imaging, displacement. Displacement is very important, and we're going to spend to assess impedance. Remember when I told you that if you have, do you know that when people do lying detector, have electrodes on the skin? Why resistance of the skin? If you're stressed, the skin is sweat. Even a little bit of it, acting with blood. But they look at also the heart rate and temperature. So all of them together collectively, they can say what is happening to them. And chemical concentrations, that is related to if you want to have blood specimen, chemical concentration, things happening there. Now, why I'm showing you this? We would like to design instruments to measure all of this, right? So medical instrumentation, we don't want to actually so you're measuring what's the body, activities are, and all these, the measurement is accessible. So if I told you I designed it like the temperature, it's easy for me to assess. If it's indirect, the measurement is inaccessible, and we need to find something that we can get that parameter from indirectly. So you need to measure something else and to map back that. For example, cardiac output. It's the blood volume per minute from the heart. We can't open the heart and look at that, but we would like to find something else that we can measure it indirectly. So your instrument is either direct or indirect. Also, morphology of internal organs and pulmonary volume, these are all indirect. Things that are inaccessible, or parameters that are inaccessible, they're important clinically, but I them. Now, you can have something called sampling and continuous modes. So you can be, let's say, measuring the body temperature the morning and at night. So you're taking samples, right? If someone is in the ICU and we need something to be monitored continuously, like the respiratory gas flow, that's a continuous mode of measurements. So those are now we need to distinguish between these two. Also, you have generating and modulating sensors. Now, generating, something that it is actually giving you the information, but modulating, similar to the example that I told you, if someone is taking a pill, right? So I'm affecting it, right, with that. So generating sensor, energy taking directly from the measurement. Modulating sensor, use the measurement. So let's say you have a cell, and actually there is a current passing through it. That's a constant. And then that current will change. So the exposure is changing what is actually already flowing inside that cell. So you can find medical instruments that they are generating, and other medical instruments that they are modulating. Analog and digital, we know this. Analog can be taking any value within a dynamic range. So let's say if I'm looking at the blood, the ECG, right? So you can have PQRSTUV, and that signal value here, that is an analog signal. If I told you that I'm going to just jump between things, levels, that's a digital signal. So I take 1, this is 2. So all the values here, they take 2. They don't have 1.5, 1.3. So that's digital now. And we're going to, why do we like to work with digital signals and data and information? Because it's accurate, repeatable, reliable, and doesn't have noise, and does not require periodic calibration. So if you are in a hospital, it's usually an analog device. Digital devices, they don't require calibration. Cool. And then you have real time and delayed time mode, and iWatch, whatever that thing is, and you're collecting data and it's sending it to your physician immediately. So that's real time. But if you're storing it and then someone else is looking at those, like an X-ray or an MRI, that's a delayed time. So all of these modes, they're modes of operation. So when you go to the hospital, you need to know what is the mode of operation of this instrument. Now, this is an example what I told you about, that photovoltaic and photoconductive. So see the one here, that is, if there is no sunlight on that solar panel, the current is going to be 0, correct? Nothing is flowing. If there is radiation on it, then we have a current or voltage. That's photovoltaic. Photoconductive cell is that you have a current that is flowing, and if you are radiating it, exposing it to radiation, that current will change. So there's a current already passing and constant. So that it's a steady state situation, and then if it's exposed to light, that is going to change. Now, what are the things or the constraints that actually from the signals that we would like to measure? This is very important. This slide is probably one of the most important slides you need to keep in mind. So the first thing, biomedical signal parameters, they're low and small, all of them, and compared to non-biomedical ones. So mechanical and electrical engineering mechanical engineers, they work with the larger quantities or values for their parameters. Now, the potentials in the body, the EMG and ECG and EEG in the micro to millivolts. So what's micro? 10 to the milli is 10 to the power minus 3. Now, the frequencies, you go from 0 frequency to 100 hertz. For example, electrical engineers, they work with 10,000, megavolts and gigavolts for the transmission lines. They work with 200 gigahertz and megahertz for their wireless communication. So we have really a small range. Because of this, the instrument that we need to design, they have to be different, and they have to be sensitive and small. And that's where the distinction comes in between biomedical and electrical engineering. Also, inaccessibility of many critical variables in living systems. That is also a critical situation. So we need to find ways to do indirect measurements because they're inaccessible. So that makes our instruments much more complicated. The physical size of many sensors, they have to be small. You can't have a big sensor and put it inside the body, right? Your sensors need to be small. So the dimensions of these sensors is an engineering problem for us. So all of these are challenges. So anyone who's doing biomedical engineering in the design and development, it's really a challenging engineering task. And that prohibits formation of proper measurement sensor interface. So if the sensor is small, the interface is small, which means my measurements is going to be really small. So I need to have a lot of amplification. Do you know what amplification means? I need to make it bigger, the signal. Now, if we did magnification or amplification, we're losing a lot of accuracy. So that's a big also challenge for us. If you go to a hospital and see all these instruments, we appreciate the people who designed them, because it's really a difficult task to get that instrument. Now, difficult to establish safe level of energy, that's another thing. Many mechanisms of tissue damage are not well understood. Heating of tissue must be limited. Fever is actually a protective mechanism of our system to kill everything, all the organisms that they are actually not from the body. But here's the problem. If fever persisted for a long time, what happens is that you are damaging your own tissue. And that's why we need to reduce the temperature, especially for babies. They cannot handle actually fever for a couple of days. So that's a big dangerous. So it's a protective mechanism, but it needs to be controlled. If it's out of control, it can damage our tissue. So heat is bad for us. Damage to tissue at modular levels can be caused by surprisingly low energy levels. So each one of us, and then another fellow smokes for 1 or 2 years, and then they develop throat cancer. So that our tolerance is different. And the only way to find out about this is to do genetic gene sequencing. Whatever we're doing, it's actually unpredictable in the human body. So what we try to do is just to get some margins there. Now, operation of instrument in the medical environment, that's another problem. The operation equipment must be reliable, easy to operate, capable of withstanding physical and abuse. I don't know if you've seen how nurses and other healthcare providers use medical instruments. That's abusive. They destroy it all the time. And then you have exposure to corrosive chemicals and body fluids. Electronic equipment must be designed to minimize electrical shock hazards. We're going to talk about those. We have macroshocks and microshocks. And a lot of people actually die in hospitals because of microshocks. And people don't know. So someone is dead, and we're looking, so there's nothing wrong there, but a microshock took place, and they got into heart arrest because of that. Must consider the safety of patient and medical personnel. So all of this in this slide here, everything here is a challenge. Every one of those is a challenge for a biomedical engineer. And that's why we are studying biomedical engineering separately from electrical and mechanical engineering, because we need to fix these problems that we do have, or challenges. I'm sharing here with you, this is a list of all the parameters that what is the standard sensor or method of measurement. I don't want you to memorize this, but I want you to have a copy of it to see how actually challenging our range of work, where we do work. We work with 2 hertz and 40 hertz, and that's very, very low in designing equipment. That's another continuation of these slides. And as I probably mentioned to you before, biomedical engineering is a huge field. If you want to really succeed, find a medical problem that you would like to solve, and then learn all the technologies around that medical problem. So if you're interested in the heart, you need to learn everything about cardiac output, the heart, and also tissue engineering of the heart, and how the heart, the cells and the tissue interacts, and what's the extracellular matrix, and all of these kind of things. So keep in mind, this is a very important, also a couple of slides for you. So there is something called the measurements of the galvanic skin response, which is the resistance of the skin. If someone is stressed, you have sympathetic and parasympathetic nervous system. Sympathetic nervous system carries signals that put your body on alert. So if someone is lying, even the slightest lie, actually they feel stress, and then that will change the skin impedance. And that's one of the ways where biomedical engineering is not just for diagnosis and treatment, it can have other applications as well. So now, variability of the measured quantity. Now here's the thing. Let's say someone is healthy, and we are measuring their heart rate that is 72 beats per minute, correct? Now, that's in the morning. Let's say in the afternoon, their heart rate will going to be 85. Right? At night, during sleeping, their heart rate will be 52. So even during the day, our parameters are actually changing. That's why we call it non-linear dynamic system. Everything in mechanical and electrical is based on designing linear dynamic systems. We have non-linear variable dynamic systems, and that's why our designs are completely different. And then between patients, as I told you, we have different tolerances and different genetic or genome. So we have different responses. Interactions among physical systems. So let's say someone is having a problem with the kidney is going to affect blood pressure, right? And then blood pressure is going to affect the heart. The heart is going to affect the, capillaries. And then someone is going to have stroke. So there's a lot of things that could happen in the human body. Feedback loops. So if I'm moving my hand this way, right, every time I'm moving it, it's the same movement, but I'm using different muscle fibers. Every time we cannot have absolute measurements. We need to have something called ranges in healthcare. And in order to have ranges, you need to do statistics and probabilities. There is no way that someone will tell you that a healthy heart rate is 72 beats per minute. That's wrong. You need to have a range. That is the only thing that we can do in healthcare. Everything else is not true. And you will find people with high blood pressure, but they're normal. And if we try to reduce the blood pressure, they get sick.